Uh, Thank you all for tuning in. And yeah, so Peter Outridge, Dr. Peter Outridge was my supervisor, and now he's retired in BC and he sends his regards. But he's not retired from me yet because I still need to defend. So this work constitutes the last chapter of my doctoral thesis. The first two chapters were also focused on Iceland, but more on these erupting volcanoes. And for this work, we're looking more at the constant, continuous gaseous emissions from Iceland's many geothermal fields. And my other supervisor, of course, is Dr. Feiyu Wang at the University of Manitoba here in Winnipeg, Canada. And yes, so basically, in terms of my project's focus, it's really volcanic mercury emissions. And this has obviously been a question for several decades because we recognize that volcanoes emit mercury as a natural source. Of course, that anthropogenic sources are much better constrained, and we've increasingly loaded the atmosphere with more anthropogenic source mercury. But the big question is how much is emitted naturally, before these anthropogenic inputs are factored in. There's been a wide range of estimates, and the major uncertainties are really due to this. There's many volcanoes and geothermal degassing areas across Earth's surface, and only about 15% we've actually taken measurements from. And of course, a lot of those measurements are just from single time points or maybe just 1 or 2 years. So the temporal variation of mercury emissions is expected to be, variable, fluctuating just as other gases like sulfur dioxide. So that's another question mark. Reliability of certain methods and data, which I believe my doctoral work has helped at least to clarify some things with certain methods and data from the past, as I'll get to at the end of this talk. But another big question mark is the geographic gaps. One of them is Iceland, and that was my area of study. Besides this, there has been ranges from just less than a ton to over 1,000 tons when you incorporate eruptive emissions from large eruptions. But the most recent work has really kind of narrowed this range down, including some work I presented at Goldschmidt in Lyon, France last July, but also work from others at MIT and in France that have just really constrained this range, which is quite nice, to about 142 to 250 tons per year. So really down here, perhaps about 1/10 of anthropogenic emissions. But, my project, as I said, is focused on Iceland. It's a very volcanic area. If any of you have been reading the news, you'll know that in the southwest part of Iceland, they've had to evacuate a fishing town because of this magma intrusion at depth that looks like it may erupt at the surface, which is quite serious. It also has one of Peter and I's favorite fish and chips restaurants in Grindavik. So we're really hoping the town is saved, for people's livelihoods and houses, but also for that amazing fish and chips restaurant. So Iceland is along the mid-Atlantic ridge, centered on a hot spot with upwelling mantle material at depth, but also this spreading ridge where new material is constantly being created. So it's a really young kind of province, igneous province, really. And it's sort of, along the northeast to southwest trending line of that mid-Atlantic ridge, you have these volcanic zones. And so we focused our work on gaseous elemental mercury emissions from these geothermal fields over 2 years. And this is just showing the geographic range. We sort of refined our method here in the southwest, and this is near where that magma intrusion and unrest is currently occurring. And then we sort of spread out the next year. Peter and I went further afield. We actually did some measurements at Aska, but we had issues with our instrument, so couldn't include that. But we have basically 6 different geothermal areas representing these different sort of systems at different parts of the island, different magma types. They're all high temperature areas. So larger, more important sources of these gases, including potentially mercury. And this is just sort of what it looks like up here in the northeast, the Namafjall geothermal field. Large areas of altered soils, some yellowish, whitish minerals, usually from sulfur, native sulfur precipitates. And we wanted to know, we did some surface measurements, but we wanted to understand, well, what's going on below the surface, just below the surface, because In Iceland, wind, the heavy winds, is a very dominant environmental feature. So we're frequently getting a kind of atmospheric contaminated signal of how much mercury is emitting from the surface, contaminated by this, very clean North Atlantic wind, about 1 to 2 nanograms per cubic meter of mercury. So very low levels, and this sort of established background levels. And so we did some in 2021 kind of sampling with our portable soil mercury sampling kit. This is our Lumex. And we sort of adapted a setup that we could sample from just these small, tiny holes that we created to get a sense of what mercury levels are like at 20 or 10 centimeters depth using this sort of rod here with these inlets that prevent flow blockage. So we figured out a method that works, and then it was establishing, well, this is actually what it looks like in the field. So you've got our hole, got your probe, and then you're reading the mercury levels in real time, and also temperature as well, which has important considerations for how much GEM you'd expect in the subsurface based on temperatures because of that dependence. So our objectives were, well, how much mercury is there in the soil compared to the surface? So we did paired measurements at these individual sampling points of surface GEM and as well as just 10 centimeter depth. So we did a shallow depth because we just chose that as being the optimal for our setup, the optimal depth. How representative is one sampling point, one sampling survey rather. So we did 2 years of sampling at 2 different sites just to see if these levels seem to vary, how trustworthy is our data. And then just in spatial terms, how representative is one sampling point? So we established these, what Peter termed microspatial variability grids. So we did 8 or 10 points within this really confined square meter grid. And this was to assess, we're doing these points across the geothermal field. Sometimes the spots are 5 or more meters apart, maybe even 10 meters apart. So we wanted to see how representative is one sampling point if we can try these microspatial variability tests. Does GEM increase with further depth? So we did additional measurements at depth at 20 centimeters. That's as far as we could go. And then what about the actual particles of the soil? How much mercury is bound to them as total mercury? So we took back each of those soil cores, retained them for analysis in the laboratory back in Manitoba. And then using these data, these paired soil and surface measurements, and also soil data, can we actually estimate a flux at each point? So how much mercury is upwelling or downwelling potentially based on the concentration gradient between those 2 points using Fick's first law. So there's a lot of different approaches because we had this instrument that was able to give us real-time data, and we decided to try to basically set up a sampling survey that would tell us different things than just concentrations. But surface GEM, so these are our results, range just at the very top of the surface with this sampling rod from 1 approximately background to 246 nanograms per cubic meter, so 200 times. But down in the subsurface in the 10 centimeters, we saw a range of just 8 to really, really high levels, 19,110 nanograms per cubic meter, which was pretty astounding. Commonly we'd see in the hundreds to low thousands, but there were obviously a few hot spots at a couple of sites. And then with all these points that we made at these different sites, we were able to use inverse distance weighting on ArcGIS to set these sort of contour maps up to show these subtle gradations of concentrations in this case across the soil surface. Now, for some of these sites, we covered as much ground as we could, but for others, such as at Namafiat, we took only a sort of smaller portion of 100 meters by 500 meters. So, there are some uncertainties inherent in upscaling to the whole geothermal system, but our, collection and density of these different points will help us mitigate some of those uncertainties in the total concentrations that we see. So that's what it kind of looks like for these different sites. Gunnekfair, Eldvorp, and Okeldehouse are down in the southwest, and these are sort of in the central and northeastern part of the country. So our interannual variability, there were, aside from this outlier here at Eldvorp, this real hot spot, we saw no significant differences between the 2 years, which was encouraging. At least showed that the system degassing as much as we could was fairly steady and stable. And then among these different points within the square meter, we saw no significant differences. So at any given point, there were no differences from one point to the other, which is kind of nice because, at each point, you're not sure, okay, what if we just move a little bit further away? How much does it vary? And at least with these 3 spots we showed. And I should note that for these 2 sites, these were 2 different small little grids, and for this site, it was just one. But yeah, it's fairly encouraging results again. And then what happens when we go deeper from 10 centimeters? So we would originally do the 10 centimeter measurement, and then we go down even further. We have our little coring, sort of a soil sampler, and then pull out the core and then measure. So in most cases, 80% of the cases, we saw higher levels at depth, at 20 centimeters depth than at 10 centimeters depth, which just shows an increasing concentration gradient with depth, which is expected. In some cases where it was higher in the shallower depth, it could be explained by, we basically a lot more atmospheric air sort of intruded into the hole and diluted the signal. But in most cases, in some cases, it's very small differences, but the concentrations of GEM were significantly higher than at the shallower depth. And then what about the soil-bound mercury? So we're not talking about gas anymore. We're talking about particle-bound soil fraction that we analyze in the laboratory. So similar to our GEM concentration hotspots, we have these kind of hotspots in particle-bound soil mercury, several of these sites. Now, what's interesting is that in some cases with the GEM soil gas at depth, the hotspot is not in the same location, which seems to suggest, at least to us, that at one point more mercury was being channeled up here and collected by the soil, and also degassed up through the surface. And then sort of these changes in the fractures and the upwelling gas pathways in these systems preferentially channeled GEM to different areas. So we have to do more work on this because it's really interesting. But some of these hotspots may be former locations of where more gas was being channeled upward. And that's typical of these geothermal systems. You have a lot of less permeable area, even though a lot of steam is still rising up from the soil. And you've got these hotspot areas of higher gases like CO2 and hydrogen sulfide. They're channeled up through cracks and fractures and these preferential pathways formed in the whole sort of geothermal edifice, so to speak. So really interesting results that we're discussing in this manuscript I'm writing up. And then we have all this concentration data. We have soil parameters. And so we can actually estimate a flux it's going to have more uncertainties compared to our raw concentration data. But we use the Fick's law, which is just basically a dispersion coefficient multiplied by the concentration gradient over depth. We get these GEM fluxes for each individual point, and they range from 0, so no flux because the dispersion coefficient is 0, to 45.4 nanograms. This is the median for each site. So there's just 6 sites. Median because the data is very log normal. So there's very few high sort of hot spots of outgassing mercury. This is evident in these outliers shown for all these different flux measurements for each 6 site. And then when we area weight the average for all 6 geothermal sites, so what's the average estimated flux in Iceland for these sites, weighted to how much area each site occupies? Because Námafjall, for instance, is way larger than Gunnarfjall, the total surface that we surveyed. That's about 9.2 nanograms per meter squared per day. It's quite low, but it's obviously higher than our estimated background GEM flux, which we obtained through non-geothermal measurements, just putting our method on just background soils. So we have these extreme outliers indicating what we think are these hot spots of enhanced mercury release. And using the inverse distance weighting algorithm, it actually allows us to estimate the area-wide total flux from our study area. And that's shown, in these maps here, these IDW maps for all 6 sites. So with House especially, there's just this one area, which is really interesting, of highest mercury in the soil, so mercury particle bound, highest GEM concentrations in the subsurface, and as a result, the highest flux. It's quite a young system, House. So perhaps this has just really been the only area that this upwelling has been occurring, versus these other sites where you see these different areas of higher soil mercury, which are not so high in the actual gas in the soil. So our context, when we have these area weighted or total area flux for these different geothermal sites, they're all, a kilogram per year or 10 kilos per year. So in the range of the tons per year, they're way down there. But importantly, they're in the range of some of these other sites like Solfatara crater or these Greece, the fumaroles from Nea Kameni. So there's just 2 sites I'm giving a kind of range here. And then when we upscale that to our total geothermal area across Iceland, which is about 530 square kilometers, our Icelandic geothermal degassing flux is about 20 kilos per year, or 0.02 tons per year. Of course, there's a lot of uncertainties inherent in these upscaling, but we feel that our spatial variability tests, our interannual variability tests, the work that we're able to do over a couple of years helps at least to show that the method works. But one of the greatest uncertainties is with the fluxes. So, for this paper that we're putting together, we're really emphasizing the interesting trends and patterns and concentrations at the surface and subsurface, and also what mercury is bound to the soil particles as well, and that kind of exchange with the gases. The flux is just sort of the last component that we're trying to formulate an estimate, because we want to, place this within this larger context of volcanic degassing of mercury from Icelandic volcanic activity. So for the geothermal activity, we see that we have these extreme enrichments in soil GEM at 10 centimeter depth, which can be tens of thousands of times higher than surface GEM. And then in the soil-bound mercury concentrations, you can see that these extreme enrichments are in some cases in the same range as highly contaminated soils near industrial point sources, such as the Flin Flon metal smelter here in Manitoba. So in the hundreds of micrograms per grams range. And of course, with this, further work is needed to understand what this means, the environmental implications of these extreme, in some cases, extreme mercury enrichments in these surface soils, especially because we know that, at least at Gaseous, one of the geothermal sites, the areas we were studying weren't the really active areas. These were formerly active areas, and we couldn't really access the more active areas because it's a big tourist site. We didn't have really access there. But the less active areas, there's less steam. The soils can be eroded more easily because it's not sort of being held in place by a lot of soil moisture. And dust storms are really common in Iceland. So there's potential for mercury mobilization in these surface soils through a lot of the dust-blown air pollution that occurs. So something that we hadn't really thought was possible, but these kind of highly contaminated but naturally sourced mercury enrichments right near the surface. But, so we're looking at the local effects, but the global scale effects are likely minor when we look at the geothermal flux, 0.02 tons per year. This is, it makes sense when we think of the few global geothermal fluxes estimates that have been published in the literature. It's usually between 1 and 8 tons per year, so quite low in context with the more persistent degassing and eruptions, which obviously propel a lot more material and gases into the atmosphere. And these are estimated, again, as I mentioned earlier, at about 150 to 250 tons per year. So a really small component of that would be geothermal degassing. And so what we see here is quite expected for this whole region entirely. So And then just as a postscript, when I started my PhD, I was looking at, okay, what do we know about mercury concentrations in Iceland? And the only real work that was done was in the 70s. And so there were some really high levels in geothermal areas in these areas during a Heme eruption off the south coast of Iceland, so up to 30,000 nanograms per cubic meter. Just keep in mind that 1 to 2 nanograms per cubic meter is the atmospheric background. So these are really, really elevated levels. But even in non-geothermal areas, so background levels, up to 800 or 1,000 nanograms per cubic meter. So this trend of really elevated mercury levels in the air was something I was expecting to see when we went to Iceland in 2019. But we saw more background levels. So this sort of adds more evidence to this argument that a lot of this data is just erroneously high, probably due to contamination issues and just less of the analytical rigor of mercury, environmental mercury analysis. So we made some major strides, and up to about 2000, some of that data is questionable. And this isn't just for atmospheric measurements in these volcanic areas, but also for in ice sheets, in ocean levels. We see this pretty substantial decrease in estimates or the reported values of mercury in these different environmental media from the 70s onward. And that's just thought to be better methods, less contamination. So we're getting much better data nowadays. And we seem to show that with this comprehensive study of Iceland, that background levels in the air, especially with all the wind action and the constant influx of North Atlantic wind, seeing background levels near the surface. But importantly, just below the surface, we do see these much higher levels. So yeah, that's kind of the gist of this work. These are the references we're using for the presentation. And I think, at least not me, but probably a follow-up student who works for FAE will probably return to one of these sites to do more in-depth measurements here. But because we saw such high enrichments of soil-bound mercury, that alone is a really interesting result. But it's sort of one of the most comprehensive soil surveys in the literature for mercury. And yeah, it just sort of points the way for future work, not only in Iceland, but these other areas where you have more accumulation chamber methods that measure the flux, but there's no actual interaction or sampling of the soil itself to understand what is the soil-bound mercury fraction. So thank you so much, Messi.